When you look up at the night sky, you see stars scattered across darkness. Between those points of light lies something we call empty space. But this emptiness is not truly empty. It holds secrets that have existed since the beginning of time itself. The silence of space is not the absence of everything. It is the presence of something so vast and so subtle that we are only beginning to understand it. Space is often described as a vacuum. This means it contains very little matter. In the space between stars, you might find only a few atoms in each cubic meter. On Earth, that same cubic meter of air contains billions and billions of atoms. So space seems empty by comparison. But emptiness and silence are not the same thing. Silence simply means we cannot hear, and in space there is no air to carry sound waves to our ears. So even if something were making noise, we would hear nothing. This silence has puzzled humans for thousands of years. Ancient peoples looked at the stars and wondered what lay beyond. They created stories to explain the lights in the sky. They imagined gods and heroes placed among the constellations, but they could not hear the universe. They could only see it, and what they saw was stillness. The stars seemed fixed in place, moving only in slow circles as the earth turned beneath them. The silence and stillness made space seem eternal and unchanging. We know now that space is neither still nor unchanging. The stars are moving at tremendous speeds. Galaxies are rushing away from each other. The universe itself is expanding, but we still cannot hear any of this motion. The silence remains, and within that silence, hidden from our ears, are phenomena that shape the cosmos in ways we are only beginning to comprehend. One of the first things to understand about space is that it is not nothing. Even in the darkest, most remote regions, far from any star or galaxy, space contains energy. This energy is built into the fabric of space itself. Scientists call it vacuum energy or dark energy. It does not shine, it does not make sound, but it exists everywhere, pushing space apart, causing the universe to expand faster and faster as time goes on. Imagine a loaf of bread baking in an oven. As it bakes, it rises. The raisins scattered through the dough move apart from each other, not because they are moving through the dough, but because the dough itself is expanding. Space works in a similar way. Galaxies are like raisins in the cosmic dough. As space expands, galaxies move apart. They are not traveling through space. Space itself is growing between them. This expansion is happening in silence. There is no sound of tearing or stretching. There is no rumble or hiss. Space simply becomes larger. And because this happens everywhere at once, we cannot point to a center or an edge. Every point in space is expanding away from every other point. If you were floating in the void between galaxies, you would see distant galaxies slowly receding in all directions, and you would hear nothing. The silence of space also hides the remnants of the universe's birth. About 13.8 billion years ago, the universe began in an event we call the Big Bang. This was not an explosion in space. It was an explosion of space itself. In the first fractions of a second, the universe expanded from something smaller than an atom to something vast. During this time, it was filled with intense energy and light. But there was no sound because sound requires matter to vibrate. And in those earliest moments, matter as we know it did not yet exist. As the universe cooled, particles formed. Protons and neutrons came together to make the first atomic nuclei. Electrons joined them to form the first atoms. These were mostly hydrogen and helium, the simplest elements. They filled space like a fog. Light could not travel far through this fog because it kept bumping into particles. The universe was bright but opaque, and it was silent. After about 380,000 years, the universe cooled enough for the fog to clear. Suddenly, light could travel freely. This light still exists today, stretched out by the expansion of space into microwave radiation. We call it the cosmic microwave background. It is the oldest light in the universe, a faint glow coming from every direction in space. When we detect this radiation, we are seeing the universe as it was when it first became transparent, and we are hearing its silence. The cosmic microwave background is very uniform. It has almost the same temperature everywhere we look, but not perfectly uniform. There are tiny variations, small differences in temperature from one region to another. These variations are extremely small, just a few parts in 100,000, but they are important. They represent the seeds of all the structure we see in the universe today. Regions that were slightly denser than average eventually collapsed under their own gravity to form galaxies. Regions that were slightly less dense became the voids between galaxies. All of this happened in silence. Gravity does not make sound. It simply pulls. Over millions and billions of years, gravity gathered matter together. Small clumps grew larger. They merged with other clumps. Eventually, the first stars ignited. These stars formed inside clouds of gas that had collapsed under gravity. As the gas compressed, it heated up. When it became hot enough, nuclear fusion began in the core. Hydrogen atoms fused together to make helium, releasing energy in the process. This energy made the stars shine. Stars do make sound, in a sense. Their interiors are filled with churning gas. Waves of pressure move through them. If you could somehow stand inside a star with ears that could survive the heat, you might hear a deep, constant roar. But in space, there is no air to carry this sound outward. So the roar stays trapped inside the star. To us watching from Earth or from a spacecraft, stars are silent. The light from stars travels through space without resistance. It crosses vast distances to reach our eyes. But the sound does not travel. This is one of the fundamental differences between light and sound. Light is an electromagnetic wave. It does not need a medium to travel through. It can cross the vacuum of space easily. Sound is a mechanical wave. It needs matter to vibrate. Without air or some other medium, sound cannot exist. So space is inherently silent, not because nothing is happening, but because there is no medium to carry the vibrations we would perceive as sound. Between the stars lies the interstellar medium. This is the gas and dust that fills the space within galaxies. It is very thin, much thinner than the best vacuum we can create on Earth. But it is not nothing. It contains atoms and molecules, ions and electrons, tiny grains of dust. These particles interact with each other. They collide. They absorb and emit light. They respond to magnetic fields. They are influenced by gravity. All of this happens in silence. In some regions, the interstellar medium is especially dense. These regions are called molecular clouds. They are cold and dark, shielding their interiors from the light of nearby stars. Within these clouds, gravity slowly pulls matter together. Over time, regions within the cloud become denser. They begin to collapse. As they collapse, they spin faster, flattening into disks. At the center of each disk, a new star begins to form. Around it, the disk may form planets. This is how solar systems are born. The process takes millions of years. It is slow and gradual, and it is silent. There is no whoosh of gas rushing inward. There is no crack as the star ignites. There is only the patient work of gravity and time. Eventually, the star begins to shine. Light pours outward, pushing against the surrounding gas. A stellar wind of particles streams away from the star. Radiation pressure and this wind gradually clear the area around the star, revealing it to the galaxy. But all of this happens without sound reaching us. The silence of space also hides violence. Stars do not live forever. They burn through their fuel at different rates depending on their mass. Small stars can burn for trillions of years, fusing hydrogen into helium slowly and steadily. Large stars burn much faster, exhausting their fuel in just a few million years. When a massive star runs out of fuel, it can no longer support itself against gravity. The core collapses in a fraction of a second. The outer layers crash inward and then rebound in a tremendous explosion called a supernova. A supernova releases as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifetime. The explosion is bright enough to outshine an entire galaxy. Material is hurled outward at a significant fraction of the speed of light. Shockwaves tear through the surrounding gas. New elements created in the star's core are scattered into space. These elements, forged in the heat and pressure of the dying star, will eventually become part of new stars, planets, and even living beings. But for all its violence, a supernova makes no sound that we can hear. If you were close enough to witness a supernova, you would be vaporized long before any sound could reach you. And if you were far enough away to survive, you would be too far for sound to travel. The explosion would happen in the silence of space. You would see the brilliant flash of light. You might detect the burst of particles and radiation, but you would hear nothing. After a supernova, what remains of the star's core can become a neutron star or a black hole. Neutron stars are incredibly dense. A teaspoon of neutron star material would weigh as much as a mountain. They spin rapidly, sometimes hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles. If these beams sweep past Earth, we detect them as pulses of radio waves. We call these objects pulsars. Pulsars are like cosmic lighthouses. Their beams sweep through space with clockwork precision. Some pulsars are so regular that they rival the best atomic clocks humans have built. But despite their regular pulses, pulsars are silent. The radiation they emit is electromagnetic, not acoustic. We can convert the pulses into sound by assigning a tone to each pulse, but this is an artificial representation. The pulsar itself makes no sound. Black holes are even more extreme. They form when a massive star's core collapses so completely that not even the pressure of neutrons can stop it. The core shrinks to a point of infinite density called a singularity, surrounded by a boundary called the event horizon. Anything that crosses the event horizon is lost forever. Not even light can escape, so black holes are not just silent, they are invisible. We can only detect black holes by their effects on nearby matter. If a black hole is part of a binary system with a normal star, it can pull gas from that star. The gas spirals inward, forming a disk around the black hole. As the gas spirals inward, it heats up due to friction and compression. It becomes so hot that it emits X-rays. These X-rays reveal the presence of the black hole, but the black hole itself remains silent and unseen. Even when black holes merge, an event of unimaginable violence, the collision is silent in the conventional sense. Two black holes orbiting each other will gradually spiral inward, losing energy by emitting gravitational waves. These are ripples in the fabric of space-time itself. As the black holes get closer, they orbit faster and faster. Finally, they merge, forming a single larger black hole. The merger releases a tremendous amount of energy in the form of gravitational waves. We detected gravitational waves for the first time in 2015. The event was the merger of two black holes more than 1 billion light-years away. The gravitational waves traveled across space at the speed of light. When they reached Earth, they caused space-time itself to stretch and squeeze by a tiny amount. Detectors designed to measure this stretching and squeezing picked up the signal. Scientists converted the signal into sound, creating a chirp that rises in pitch and volume before ending abruptly. But this sound is a representation. The actual event produced no sound waves. It produced gravitational waves, which are a completely different phenomenon. Gravitational waves are one of the hidden aspects of space's silence. They carry information about violent cosmic events. Merging black holes, colliding neutron stars, supernova explosions, and even the Big Bang itself produce gravitational waves. These waves travel through space, passing through matter and energy, without being absorbed or scattered. They are almost impossible to detect because they cause such tiny changes in distance, but with sensitive enough instruments, we can detect them, and when we do, we learn about events that would otherwise remain hidden in silence. The space between galaxies is even emptier than the space between stars. Galaxies are separated by millions or even billions of light years. In these vast voids, there is almost nothing. A few stray atoms, a faint glow from the cosmic microwave background, the occasional wandering photon of starlight, and dark matter. Dark matter is one of the greatest mysteries in science. We cannot see it. It does not emit light or any other form of electromagnetic radiation. It does not interact with normal matter except through gravity, but it is everywhere. There is about 5 times as much dark matter in the universe as there is normal matter. Dark matter forms a kind of invisible scaffolding that holds galaxies together and shapes the large-scale structure of the universe. We know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the amount of visible matter they contain. Clusters of galaxies hold together more tightly than the gravity of their visible matter can explain. Light from distant galaxies is bent by the gravity of intervening matter, and the amount of bending indicates more mass than we can see. All of these observations point to the presence of dark matter. But what is dark matter made of? We do not know. It could be made of particles that have not yet been discovered. It could be something even stranger. Scientists have proposed many candidates, from weakly interacting massive particles to primordial black holes. Despite decades of searching, we have not yet detected dark matter directly. It remains hidden in the silence of space, exerting its influence through gravity alone. Dark energy is even more mysterious. While dark matter pulls things together through gravity, dark energy pushes things apart. It is the force driving the accelerated expansion of the universe. It makes up about 70% of the total energy content of the universe, yet we have no idea what it is. We only know that it exists because we can measure its effects. In the late 1990s, astronomers studying distant supernovae made a surprising discovery. They expected to find that the expansion of the universe was slowing down over time due to the gravitational pull of all the matter it contains. Instead, they found that the expansion is speeding up. Something is counteracting gravity on the largest scales, pushing galaxies apart faster and faster. We call this something dark energy. Dark energy appears to be a property of space itself. As space expands, more dark energy comes into existence because it is tied to the volume of space. This creates a feedback loop. The more space expands, the more dark energy there is. The more dark energy there is, the faster space expands. If this continues, the universe will expand forever, becoming colder, darker, and emptier as time goes on. All of this happens in silence. The acceleration of the universe's expansion makes no sound. Dark energy exerts no pressure waves. It simply exists, woven into the fabric of space, driving the cosmos apart. We detect it only through careful measurements of distant galaxies and supernovae. Without these observations, we would never know it was there. The silence of space hides these enormous forces and vast quantities of invisible matter and energy. When we look at the night sky, we see only a small fraction of what exists. Most of the universe is hidden from our eyes, and all of it is hidden from our ears. Within our own solar system, the silence is just as profound. The sun pours out energy in all directions. Particles stream away from it in the solar wind. Planets orbit in their paths. Moons circle planets. Asteroids and comets follow their own orbits. Dust grains drift through the space between worlds, but none of this makes sound that we can hear. The sun itself is a churning ball of plasma. Its interior is filled with convection currents as hot gas rises and cooler gas sinks. The surface, called the photosphere, is covered with granules marking the tops of these convection cells. Above the surface, the chromosphere and corona are even more active, with loops and flares of superheated gas following magnetic field lines. All of this activity involves motion and energy, but in the vacuum of space, there is no air to carry sound waves away from the sun. Solar flares and coronal mass ejections are among the most violent events in the solar system. A solar flare is a sudden release of magnetic energy, causing a bright flash of light and a burst of radiation. A coronal mass ejection hurls billions of tons of plasma into space. If directed toward Earth, these events can cause auroras and disrupt satellites and power grids, but they are silent. We see the flash, we detect the radiation, we feel the effects, but we hear nothing. The solar wind is a constant stream of charged particles flowing outward from the sun. It fills the solar system, pushing against the magnetic fields of planets, shaping the tails of comets and eventually reaching the boundary where the sun's influence fades and interstellar space begins. This boundary is called the heliopause. Two spacecraft, Voyager 1 and Voyager 2, have crossed this boundary and entered interstellar space. They are now farther from Earth than any other human-made objects, and they travel through silence. Planets move through space without sound. Earth orbits the Sun at about 30 kilometers per second. That is fast enough to circle the Earth in just a few minutes, but there is no whoosh of air, no sonic boom. There is only the silent motion of a world through the vacuum. If you could stand on an asteroid and watch Earth pass by, you would see it gliding silently across the blackness. Moons orbit planets in the same silence. Our moon circles Earth once every 27 days. Its gravity pulls on Earth, causing tides in the oceans. Earth's gravity pulls back, keeping the moon in its orbit. The two worlds are locked in a gravitational dance that has lasted for billions of years. But the dance is silent. There is no music, no rhythm that we can hear. Only the patient pull of gravity guiding their motion. Asteroids occasionally collide. When they do, the impact can be violent. Rock smashes into rock at speeds of kilometers per second. Fragments are thrown in all directions. Craters form. Heat and shock waves spread through the colliding bodies, but all of this happens in silence. There is no crash, no bang. The impact is felt, not heard. Comets are travelers from the outer solar system. They spend most of their time far from the sun, in the cold and dark. But their orbits sometimes bring them close to the sun's warmth. When they approach, the ice in the comet begins to vaporize. Gas and dust stream away, forming a glowing coma around the nucleus and a tail that can stretch for millions of kilometers. The comet becomes visible from Earth, a faint smudge in the night sky. But it is silent. The vaporizing ice makes no hiss. The streaming gas makes no sound. Even within a planet's atmosphere, space remains nearby, and its silence is just above. On Earth, sound travels easily through the air. We hear wind, thunder, the roar of engines, the song of birds. But if you could rise up through the atmosphere, the air would grow thinner and thinner. Sound would become fainter. At a certain altitude, the air would be too thin to carry sound effectively. Eventually, you would cross an invisible boundary where sound can no longer travel. You would enter the realm of silence. This is the edge of space, often defined as 100 kilometers above sea level. At this altitude, the atmosphere is so thin that it barely exists. Satellites orbit here, circling Earth in silence. Astronauts aboard the International Space Station live and work in this silence. When they venture outside on a spacewalk, they can see Earth turning below them. They can see the stars shining steadily without the twinkling caused by Earth's atmosphere. They can see the sun's harsh light, but they hear nothing except their own breathing and the sounds transmitted through their suits. Astronauts have described space as profoundly quiet. Without air to carry sound, the usual background noise of life disappears. There is no rustling of leaves, no hum of machinery, no chatter of voices unless transmitted by radio. Even the vibrations that travel through a spacecraft's structure are muffled by the vacuum outside. The silence is total and absolute. It is a silence that can be unsettling, a reminder of the vast emptiness that surrounds our fragile world. But space is not truly empty, and it is not truly silent in every sense. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays all travel through space. These are different forms of electromagnetic radiation, each with its own wavelength and energy. They do not make sound, but they carry information. By detecting and analyzing this radiation, we learn about the universe. Radio telescopes capture radio waves from space. These waves can come from many sources. Pulsars emit regular pulses of radio waves. Supernova remnants glow with radio emission. Galaxies emit radio waves from the regions around their central black holes. Even the cosmic microwave background is a form of radio emission. Radio telescopes allow us to see the universe in a way our eyes cannot. They reveal phenomena hidden in the silence, processes that involve energy and motion but produce no sound. Infrared telescopes detect heat. They show us the warm glow of dust clouds where stars are forming. They reveal planets orbiting other stars by the heat they emit. They peer through the dust that blocks visible light, showing us the centers of galaxies and the hearts of stellar nurseries. Infrared light is invisible to our eyes, but it is there, traveling through space carrying information. Ultraviolet, X-ray and gamma-ray telescopes detect even higher energy radiation. These forms of light come from the hottest and most energetic processes in the universe. X-rays are emitted by gas heated to millions of degrees as it falls into a black hole. Gamma rays are produced by supernova explosions and by matter and antimatter annihilating each other. This high-energy radiation is absorbed by Earth's atmosphere, so we must use space-based telescopes to detect it. But once detected, it tells us about events of incredible violence and energy, all happening in silence. Neutrinos are another messenger from the cosmos. These are tiny, nearly massless particles that interact very weakly with matter. They can pass through entire planets without being stopped. Trillions of neutrinos from the Sun pass through your body every second, but you do not feel them. They are produced by nuclear reactions in the cores of stars and by supernova explosions. Detecting neutrinos is extremely difficult, but when we do, they provide unique information about processes happening deep inside stars and in the most violent cosmic events. Gravitational waves, as mentioned earlier, are ripples in space-time. They are produced by accelerating masses, especially very massive objects moving at high speeds. Merging black holes and neutron stars are the strongest sources of gravitational waves we have detected so far. These waves carry information about the masses, spins, and distances of the objects that produce them. They travel through space without being absorbed or scattered, providing a clear signal even from events billions of light years away. All of these messengers, electromagnetic radiation, neutrinos, gravitational waves, travel through the silence of space. They allow us to sense the universe beyond what our eyes and ears can perceive. They reveal a cosmos full of activity, energy, and change. But none of them make sound. The universe communicates with us in many ways, but not through sound waves. There is another aspect of silence in space that is worth considering. It is the silence of time. Events in space often unfold over timescales that are almost incomprehensible to humans. Stars form over millions of years. Galaxies collide and merge over billions of years. The universe has been expanding for nearly 14 billion years. These processes are so slow that even if they made sound, it would be a sound that changes over eons, a note so low and slow that we could never hear it. Consider a galaxy slowly spiraling into a larger galaxy. The process takes hundreds of millions of years. Stars from both galaxies pass through each other, almost never colliding because the distances between stars are so vast. But the gravitational interaction distorts both galaxies, pulling out long streamers of stars and gas. Eventually, the smaller galaxy is absorbed and the larger galaxy grows. If this process made sound, it would be a sound that changed so slowly that countless human lifetimes would pass between one note and the next. Or consider the slow dimming of a star. Stars like the Sun will eventually exhaust their hydrogen fuel. They will swell into red giants, then shed their outer layers, leaving behind a hot, dense core called a white dwarf. The white dwarf will cool slowly over trillions of years, fading from white to yellow to red to black. If this fading made sound, it would be a sound that dropped in pitch so gradually that the change would be imperceptible across thousands of generations. The silence of space is not just the absence of sound, it is also the absence of hurry. The universe operates on timescales that dwarf human experience. Stars live and die. Galaxies form and evolve. The universe expands and cools. All of this happens slowly, patiently, without urgency. The silence reflects this patience. It is a silence that speaks of deep time, of processes that unfold across ages, of a cosmos that has no need to rush. This perspective can be comforting. In our daily lives, we are surrounded by noise and urgency. We are constantly reacting to immediate demands. But when we think about space, we step back from that immediacy. We contemplate processes that have been going on for billions of years and will continue for billions more. We see our own lives as brief moments in a vast timeline, and in that vastness, there is a kind of peace. The silence of space also invites us to listen more carefully to what is actually there. When there is no sound, we pay more attention to other signals. We watch the light from distant stars and galaxies. We measure the radiation that reaches us. We detect the faint ripples of gravitational waves. We piece together the story of the universe from these subtle clues. The silence forces us to be patient and attentive observers. In a way, the silence is a gift. It removes distractions. It allows us to focus on what matters. It teaches us to see and to think rather than just to hear. And it reminds us that the universe does not exist for our entertainment. It simply is. It follows its own laws and rhythms, indifferent to our need for noise and excitement. There is also a philosophical dimension to the silence of space. For much of human history, we believed that the universe was perfect and unchanging. The heavens were seen as a realm of eternal order, separate from the chaotic, changing earth. The silence of space reinforced this idea. If the heavens made no sound, perhaps they were indeed still and perfect. But we now know that the universe is dynamic and ever-changing. Stars are born and die. Galaxies collide. The universe expands. The silence does not mean stillness. It simply means that the motion and change happen in a medium that cannot carry sound. The realization that the universe is active and evolving, even in silence, changed our understanding of our place in the cosmos. We are part of this changing universe. The atoms in our bodies were forged in stars. The calcium in our bones, the iron in our blood, the carbon in our cells, all of these elements were created in stellar cores or in supernova explosions. We are made of stardust, and the processes that created us happened in the silence of space over billions of years. This connection to the cosmos is humbling and awe-inspiring. We are not separate from the universe. We are a part of it. The silence that surrounds us in space is the same silence that surrounded the formation of the elements that make us up. It is a silence that has witnessed the entire history of the universe, from the Big Bang to the present moment. When we send spacecraft into space, they travel through this silence. They carry instruments to measure and observe. They send back data as radio signals, which we receive on Earth. These signals travel at the speed of light, but they are not sound. They are electromagnetic waves. encoded with information. We decode the signals and learn what the spacecraft has discovered. But the spacecraft itself moves through silence, a tiny human-made object in the vastness of space. Some spacecraft carry messages for any potential extraterrestrial intelligence that might find them. The Voyager spacecraft each carry a golden record, a phonograph record with sounds and images from Earth. There are greetings in many languages. There is music, from Bach to Blind Willie Johnson. There are natural sounds, waves breaking, wind blowing, birds singing. These sounds represent the diversity and richness of life on Earth. But they are trapped on the record. In the silence of space, they cannot be heard unless someone finds the record and figures out how to play it. This act of sending a message into space is both hopeful and poignant. It is an acknowledgement that we are alone in the silence, at least for now. We have not yet detected any signals from other civilizations. We have not found any evidence of life beyond Earth. The silence of space extends to the realm of biology as well. As far as we know, the universe is mostly lifeless. And where there is no life, there is no sound except the natural processes of physics and chemistry. The search for extraterrestrial intelligence, known as SETI, involves listening for radio signals from other civilizations. Radio telescopes scan the sky, looking for patterns that could indicate an artificial source. So far, we have heard nothing. The cosmos remains silent, at least on the frequencies we have been monitoring. This silence raises deep questions. Are we alone? Is intelligent life so rare that we are the only example in the galaxy? Or are there other civilizations out there also listening, also surrounded by silence? If we ever do detect a signal, it will be a momentous event. It will mean that the silence has been broken, not by natural processes but by another intelligence. It will mean that we are not alone. But until that day, we continue to listen, surrounded by the silence of space, wondering what it hides. The silence also plays a role in how we experience space exploration. Astronauts and mission controllers communicate by radio. When an astronaut speaks, their voice is converted into radio waves and transmitted to Earth. The radio waves travel at the speed of light, but there is a delay. For astronauts on the Moon, the delay is about 1.3 seconds each way. For spacecraft farther out, the delay can be minutes or even hours. This delay creates a strange kind of silence, a gap in conversation that reminds us of the distances involved. When we watch footage of spacewalks or landings on other worlds, we see the action, but the sound is added later. The original events happen in silence. The crunch of boots on lunar soil, the hum of machinery, the voices of astronauts, all of these are recorded inside their suits or spacecraft and transmitted separately. Without this audio, we would watch in silence, seeing the motion, but hearing nothing. It is a reminder that space is a different kind of environment, one where our usual senses are limited. The silence of space also affects how we imagine the future. If humans are to live and work in space for extended periods, we will need to create habitats where sound can travel. We will need air to breathe and to carry sound. Inside a spacecraft or a space station, there will be the familiar sounds of life, voices, footsteps, the hum of ventilation systems. But just outside the walls, there will be silence. This contrast will be a constant reminder of the thin barrier between life and the void. In science fiction, space battles are often depicted with roaring engines and exploding ships. Lasers hiss, missiles whoosh, and debris clatters against hulls. But in reality, a space battle would be silent. Explosions would produce no sound, weapons would fire without a bang, ships would maneuver without a roar. The only sounds would be those inside the ships themselves, transmitted through the hull and the air inside. Outside, there would be only the silent flash of energy weapons and the silent tumble of debris. This reality is less dramatic than fiction, but it is more profound. It forces us to confront the true nature of space. It is a place where our usual rules do not apply. It is a place that is beautiful and terrible, vast and empty, full of energy and utterly silent. Understanding this silence is part of understanding space itself. The silence of space has inspired art, music, and philosophy. Composers have tried to capture the vastness and stillness of space in music. Writers have contemplated the loneliness and wonder of the void. Philosophers have pondered what it means to exist in a universe that is mostly empty and mostly silent. These reflections remind us that space is not just a scientific subject, it is also a source of meaning and inspiration. There is a piece of music called 4:33 by John Cage. It consists of 4 minutes and 33 seconds of silence. The performer sits at a piano but does not play. The audience hears only the ambient sounds of the concert hall, the rustle of programs, the shifting of seats, the breathing of people. The piece challenges our ideas about music and sound. It asks us to consider silence as something meaningful in itself. In a similar way, the silence of space is meaningful. It is not the absence of everything. It is the presence of a particular kind of environment, one that does not support sound, but supports many other phenomena. As we learn more about the universe, we find more things hidden in the silence. Dark matter and dark energy are just two examples. There may be other forms of matter and energy that we have not yet discovered. There may be processes and phenomena that we cannot yet imagine. The silence of space is vast, and we have only begun to explore it. Our instruments are becoming more sensitive. Our telescopes can see fainter objects and detect more subtle signals. Our detectors can pick up gravitational waves from events billions of light years away. Each new discovery reveals something that was hidden in the silence, and each discovery raises new questions. The more we learn, the more we realize how much we do not know. This is the essence of science. It is a process of asking questions and seeking answers. It is a way of listening to the universe, even when the universe is silent. It is a way of finding patterns and meaning in the data we collect. And it is a reminder that the universe is vast and complex, full of mysteries waiting to be uncovered. The silence of space is hiding something huge. It is hiding the majority of the universe's matter and energy. It is hiding the processes that shape galaxies and drive the expansion of the universe. It is hiding the potential for life on other worlds. It is hiding the ultimate fate of the cosmos. And it is hiding countless other secrets that we have not yet thought to ask about. But the silence is not impenetrable. We have tools and methods to probe it. We have curiosity and intelligence to guide our exploration. And we have time. The universe is patient, and so must we be. We will continue to listen, to observe, to measure, and to think. We will continue to uncover the secrets hidden in the silence. As we do, we will come to understand more about the universe and our place in it. We will learn how galaxies form and evolve. We will discover whether life exists beyond Earth. We will unravel the nature of dark matter and dark energy. We will trace the history of the universe from the Big Bang to the present and beyond. And we will do all of this by paying attention to what the silence reveals. The silence of space is not empty. It is full of information, full of potential, full of wonder. It is a silence that invites us to look and listen more carefully. It is a silence that challenges us to think deeply and to imagine boldly. It is a silence that connects us to the cosmos and to the long history of the universe. And so we continue our journey, traveling through the silence, seeking to understand what it hides. We build telescopes and spacecraft. We send probes to distant worlds. We analyze the light from faraway galaxies. We detect the ripples in space-time. We search for signals from other civilizations. And through it all, we are surrounded by silence, a silence that is both a barrier and a doorway, hiding the universe's secrets and inviting us to discover them. In this first chapter, we have explored the nature of cosmic silence. We have seen that silence does not mean emptiness or inactivity. It simply means that the medium for carrying sound is absent. Space is filled with matter and energy, with motion and change. It is a dynamic, evolving system, but it is a system that operates in silence, beyond the reach of our ears. We have considered the expansion of the universe, driven by dark energy. We have thought about the cosmic microwave background, the afterglow of the Big Bang. We have explored the life cycles of stars, from their formation in molecular clouds to their deaths in supernovae. We have contemplated black holes and neutron stars, gravitational waves and neutrinos, radio waves and gamma rays, and we have reflected on the philosophical and emotional dimensions of silence. As we move forward, we will delve deeper into what the silence is hiding. We will explore the nature of dark matter and dark energy in more detail. We will consider the search for life beyond Earth and what the silence might tell us about our chances of finding it. We will think about the future of the universe and how the silence will evolve as the cosmos ages. And we will continue to marvel at the vastness and mystery of the universe, hidden in the silence of space. The universe is built on structures that remain invisible to our eyes. When we look at the night sky, we see individual stars scattered across darkness. We might notice a few fuzzy patches that turn out to be galaxies, but we cannot see the underlying framework that connects everything. This framework exists in the silence of space, shaping the cosmos in ways we are only beginning to understand. Imagine a vast web stretching across the universe. This web is made of dark matter, the mysterious substance that does not emit light. Along the strands of this web, galaxies cluster together. Between the strands lie enormous voids, regions where almost nothing exists. This is the cosmic web, the largest structure in the universe. It formed over billions of years as gravity pulled matter together, and it formed in complete silence. The cosmic web began to take shape shortly after the Big Bang. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds planted by quantum fluctuations in the first moments of existence. As time passed, gravity amplified these small differences. Regions that were slightly denser attracted more matter. Regions that were slightly less dense lost matter to their denser neighbors. Over millions of years, these density variations grew. The denser regions became even denser. They pulled in surrounding matter, creating clumps and filaments. The less dense regions became voids, emptying out as their matter was drawn away. Eventually, a pattern emerged, a network of filaments connecting dense nodes with vast empty spaces in between. This pattern is the cosmic web. The cosmic web spans the entire observable universe. It is hundreds of millions of light years across. If you could see it from outside, it would look like foam or like the structure of a sponge. Galaxies are embedded in the densest parts of the web, where filaments intersect. The voids between filaments contain very little matter, just a few stray atoms and the ever-present dark energy. This structure formed without making any sound. Gravity pulled matter together slowly and steadily. There were no sudden collapses, no dramatic crashes, just the patient work of attraction over vast expanses of time and space. The result is the largest organized structure we know of, built in silence. To understand the cosmic web, we must understand dark matter more deeply. Dark matter is called dark because it does not interact with light. It does not emit, absorb, or reflect electromagnetic radiation. This makes it invisible to our telescopes. We can only detect it through its gravitational effects on visible matter. The evidence for dark matter is overwhelming. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster, a group of galaxies bound together by gravity. He measured how fast the galaxies were moving within the cluster. If the cluster contained only the matter he could see, the galaxies would be moving too fast to stay bound. They should have flown apart long ago, but they remain together. Zwicky concluded that there must be much more matter in the cluster than he could see. He called this unseen matter dark matter. Later observations confirmed and extended this finding. Astronomer Vera Rubin studied the rotation of spiral galaxies. Stars in the outer regions of these galaxies orbit the galactic center. According to the laws of gravity, stars farther from the center should orbit more slowly than stars closer in, just as planets farther from the Sun orbit more slowly. But Rubin found that stars in the outer regions orbit just as fast as those closer in. This should not be possible unless there is additional mass in the galaxy that we cannot see. The rotation curves of galaxies are flat. They do not drop off as expected. This flatness indicates that galaxies are embedded in large halos of dark matter. These halos extend far beyond the visible stars and gas. They contain most of the galaxy's mass. The visible matter we see is just a small fraction of what is actually there. Gravitational lensing provides another line of evidence. When light from a distant galaxy passes near a massive object, the gravity of that object bends the light's path. This bending can magnify and distort the image of the distant galaxy. By studying these distortions, astronomers can map the distribution of mass in the intervening object, even if that mass is invisible. These maps reveal dark matter halos around galaxies and clusters. They show that dark matter is distributed in specific patterns following the cosmic web. The cosmic microwave background also provides evidence. The tiny temperature variations in this ancient light correspond to density variations in the early universe. By analyzing these variations, scientists can determine how much normal matter and dark matter existed in the early universe. The results show that dark matter makes up about 85% of all matter. Normal matter, the stuff we are made of, accounts for only about 15%. Despite all this evidence, we still do not know what dark matter is made of. Many theories have been proposed. One possibility is that dark matter consists of weakly interacting massive particles, or WIMPs. These particles would have mass, so they would exert gravity. But they would interact only very weakly with normal matter, making them nearly impossible to detect directly. Scientists have built sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch a WIMP interacting with normal matter. So far, these experiments have not detected anything conclusive. Another possibility is that dark matter is made of axions, hypothetical particles that are much lighter than WIMPs. Axions would be produced in huge quantities in the early universe and could form a kind of condensate that pervades space. Experiments are underway to search for axions, but they too have not yet found definitive evidence. Some scientists have proposed that dark matter is made of primordial black holes that formed in the early universe from density fluctuations. These black holes would be small, perhaps the mass of a mountain compressed into a space smaller than an atom. They would exert gravity but emit no light. However, observations have placed strict limits on how many primordial black holes can exist. They cannot account for all the dark matter. There are even more exotic proposals. Some theories suggest that dark matter is not made of particles at all, but is instead a modification of gravity. According to these theories, gravity behaves differently on large scales than we expect. This different behavior produces the effects we attribute to dark matter. However, modified gravity theories have difficulty explaining all the observations. They struggle to match the detailed patterns seen in gravitational lensing and the cosmic microwave background. The mystery of dark matter remains unsolved. This invisible substance makes up the majority of the universe's matter. It shapes the cosmic web. It holds galaxies together. It influences the formation of structure on all scales. Yet we cannot see it, touch it, or directly detect it. It exists in the silence of space, known only through its gravitational influence. Dark energy is an even deeper mystery. While dark matter pulls things together, dark energy pushes them apart. It is the force behind the accelerated expansion of the universe, and it makes up about 70% of the total energy content of the cosmos. This means that dark energy dominates the universe. It determines the ultimate fate of everything. The discovery of dark energy was unexpected. In the late 1990s, two teams of astronomers were studying type Ia supernovae. These supernovae are useful for measuring cosmic distances because they all have about the same intrinsic brightness. By comparing their apparent brightness to their intrinsic brightness, astronomers can calculate how far away they are. By measuring their redshift, astronomers can determine how fast they are moving away from us due to the expansion of the universe. The teams expected to find that distant supernovae were receding more slowly than nearby ones, indicating that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite. Distant supernovae were receding faster than expected. The expansion of the universe was not slowing down. It was speeding up. This was a shocking result. It implied that some form of energy was counteracting gravity on cosmic scales. This energy had to be spread throughout space, and it had to be repulsive rather than attractive. Scientists named it dark energy, echoing the term dark matter. But dark energy is fundamentally different from dark matter. Dark matter clumps together under gravity. Dark energy is smooth and uniform, filling all of space equally. The simplest explanation for dark energy is that it is the energy of empty space itself. Quantum mechanics tells us that even a vacuum is not truly empty. It is filled with fluctuating fields. Particles and antiparticles constantly pop into and out of existence in brief flickers. These fluctuations have energy. This energy could be what we call dark energy. However, there is a problem. When physicists calculate the energy of empty space using quantum mechanics, they get a number that is enormously larger than the observed value of dark energy. The calculation gives a result that is 10 to the power of 120 times larger than what we observe. This is called the cosmological constant problem. It is one of the biggest unsolved problems in physics. Despite this problem, the cosmological constant remains the leading explanation for dark energy. The cosmological constant is a term that can be added to Einstein's equations of general relativity. It represents a constant energy density that fills all of space. As space expands, the total amount of dark energy increases because there is more space, each bit of which carries the same energy density. This creates a kind of runaway effect. The more space expands, the more dark energy there is. The more dark energy there is, the faster space expands. If dark energy is truly a cosmological constant, it will dominate the universe forever. The expansion will continue to accelerate. Distant galaxies will recede faster and faster. Eventually, they will recede so fast that their light can no longer reach us. They will disappear beyond a cosmic horizon. The observable universe will shrink, even as the actual universe grows larger. In the far future, only the galaxies in our local group will remain visible. Everything else will be lost beyond the horizon, hidden by the expansion of space. But dark energy might not be constant. It might change over time. Some theories propose that dark energy is a dynamic field, similar to the Higgs field or the inflaton field, thought to have driven the rapid expansion in the first moments after the Big Bang. This dynamic dark energy could strengthen or weaken as the universe evolves. If it weakens, the expansion might eventually slow down. If it strengthens, the expansion could accelerate even faster, leading to a big rip where space expands so rapidly that it tears apart galaxies, stars, planets, and eventually atoms themselves. Observations are trying to determine whether dark energy is constant or changing. By measuring the expansion rate of the universe at different times in its history, astronomers can track how dark energy has behaved. So far, the observations are consistent with a cosmological constant. But the measurements are not yet precise enough to rule out small changes over time. Future surveys will measure the expansion history with greater accuracy, helping to narrow down the nature of dark energy. The silence of space hides both dark matter and dark energy. These two components make up 95% of the universe. Normal matter, the atoms that make up stars, planets, and people, accounts for only 5%. We live in a universe dominated by things we cannot see and do not understand. This is a humbling realization, yet we are not entirely blind. We can infer the presence of dark matter and dark energy from their effects. We can map the cosmic web by observing how galaxies are distributed. We can measure the expansion of the universe by studying distant supernovae. We can detect the bending of light by dark matter halos. We can analyze the cosmic microwave background to learn about the early universe. All of these observations tell us about the hidden components of the cosmos. The cosmic web is not static. It is constantly evolving. Over time, gravity continues to pull matter together. Filaments grow denser, voids grow emptier. Galaxies within the filaments interact and merge. Clusters of galaxies, the largest bound structures in the universe, grow larger as they attract more galaxies. This evolution happens slowly over billions of years, but it happens in a consistent direction, driven by the silent force of gravity. Within the cosmic web, galaxies are not distributed randomly. They tend to cluster together. The densest parts of the web contain galaxy clusters, collections of hundreds or thousands of galaxies bound together by their mutual gravity. These clusters are immense. They can be millions of light years across. They contain not only galaxies, but also vast amounts of hot gas trapped by the cluster's gravity. This gas is so hot that it emits X-rays. When we observe galaxy clusters in X-rays, we see the glow of this superheated gas filling the space between galaxies. The hot gas in galaxy clusters provides more evidence for dark matter. The gas should be hot enough to escape the cluster's gravity based on the mass of the visible galaxies alone, but it remains trapped. This means there must be additional mass holding it in place. That additional mass is dark matter. By measuring the temperature and distribution of the hot gas, astronomers can estimate the total mass of the cluster and determine how much is dark matter. Galaxy clusters are connected by filaments of the cosmic web. These filaments are made mostly of dark matter, with some normal matter mixed in. The normal matter is mostly hydrogen and helium gas, the same elements that make up most of the universe's ordinary matter. This gas is spread very thinly along the filaments. It is so diffuse that it emits almost no light, but it can be detected through its absorption of light from background objects. When light from a distant quasar passes through a filament, the gas absorbs specific wavelengths, leaving dark lines in the quasar's spectrum. These absorption lines reveal the presence and properties of the gas. The filaments of the cosmic web funnel gas toward galaxy clusters. As gas flows along a filament, it gradually falls into the gravitational wells created by clusters and individual galaxies. This infall of gas provides the raw material for star formation. Galaxies grow by accreting gas from the cosmic web. The gas settles into a rotating disk around the galaxy. It cools and condenses into clouds. Within those clouds, stars form. This process continues over billions of years, allowing galaxies to grow and evolve. But not all galaxies are actively forming stars. Some galaxies have used up or lost most of their gas. These galaxies are quiet, with little or no ongoing star formation. They tend to be older, redder, and more elliptical in shape. They are often found in the densest environments, such as the centers of galaxy clusters. In these crowded regions, galaxies interact frequently. They can collide and merge. They can strip gas from each other through gravitational interactions. These processes can shut down star formation, leaving the galaxy quiescent. Other galaxies are still actively forming stars. These tend to be bluer and more irregular or spiral in shape. They are often found in less dense environments, along the filaments of the cosmic web, or in smaller groups. These galaxies have access to fresh gas flowing in from the cosmic web. As long as gas continues to flow in, star formation can continue. The balance between gas inflow and star formation determines how quickly a galaxy grows and evolves. The cosmic web also plays a role in the formation of supermassive black holes. Almost every large galaxy has a supermassive black hole at its center. These black holes can have masses millions or even billions of times the mass of the Sun. They are so massive that their gravity affects the entire galaxy. Gas swirling around a supermassive black hole can heat up and emit enormous amounts of radiation, creating some of the brightest objects in the universe: quasars and active galactic nuclei. The formation of supermassive black holes is not fully understood. They likely began as smaller black holes in the early universe and grew over time by accreting gas and merging with other black holes. The cosmic web may have helped by funneling gas toward the centers of galaxies, feeding the growing black holes. As gas falls into a black hole, it forms an accretion disk. The disk heats up due to friction and compression, reaching temperatures of millions of degrees. At these temperatures, the disk emits intense radiation, including visible light, ultraviolet, and X-rays. This radiation can have a profound effect on the galaxy. It can heat the surrounding gas, preventing it from cooling and forming stars. It can drive powerful winds that push gas out of the galaxy entirely. This feedback from the supermassive black hole can regulate star formation, preventing the galaxy from using up all its gas too quickly. The black hole and the galaxy grow together, influencing each other in a delicate balance. The cosmic web extends beyond individual galaxies and clusters. On the largest scales, it divides the universe into distinct regions. Superclusters are vast collections of galaxy clusters connected by filaments. They can be hundreds of millions of light-years across. The Laniakea supercluster, for example, contains the Virgo cluster, the local group which includes the Milky Way, and many other clusters and groups. All of these structures are gravitationally connected, moving together through space. Between superclusters lie the voids. These are regions where very few galaxies exist. They are not completely empty, but they contain far less matter than the filaments and clusters. The voids can be hundreds of millions of light-years across. They are the largest underdense regions in the universe. Within the voids, space is expanding more freely, less hindered by the gravitational pull of matter. The voids are growing slowly as the expansion of the universe continues. The distribution of matter in the cosmic web is not random. It is a reflection of the initial conditions of the universe and the laws of physics that govern how matter interacts. By studying the cosmic web, cosmologists can test their theories about the early universe and the nature of dark matter and dark energy. Computer simulations can recreate the formation of the cosmic web, starting from the tiny density fluctuations in the early universe and following the evolution of matter over billions of years. These simulations reproduce the observed structure of the cosmic web remarkably well, providing strong support for the current cosmological model. Yet the cosmic web is just one aspect of the hidden architecture of the universe. There are other structures and patterns, some of which we are only beginning to discover. For example, astronomers have found evidence for gravitational waves from the early universe, ripples in space-time created by processes in the first moments after the Big Bang. These primordial gravitational waves have not yet been directly detected, but they may have left an imprint on the cosmic microwave background. Future observations may reveal this imprint, providing a new window into the earliest moments of cosmic history. There are also structures on smaller scales that are hidden in the silence. Within galaxies, there are streams of stars, remnants of smaller galaxies that were torn apart and absorbed. These streams are faint and difficult to detect, but they reveal the history of galactic growth. The Milky Way itself is surrounded by streams from disrupted dwarf galaxies. By studying these streams, astronomers can reconstruct the past interactions and mergers that shaped our galaxy. Within the Milky Way, there is also a population of dark matter particles moving through space. If dark matter is made of particles, then countless dark matter particles are passing through Earth every second. They pass through the walls of buildings, through our bodies without interacting. They are completely silent and invisible, but they are there, contributing to the gravitational pull that holds the galaxy together. Experiments deep underground are trying to detect these particles by catching one of the rare interactions with normal matter. So far, no conclusive detection has been made, but the search continues. Dark matter may also form smaller structures within galaxies. Simulations predict that dark matter should clump together on many scales, forming halos within halos. These smaller halos, called subhalos, could contain their own populations of stars, forming dwarf galaxies too faint to see, or they could be completely dark, containing only dark matter and no stars at all. Observations have found some evidence for these subhalos, but many predicted by simulations have not been detected. This discrepancy is one of the puzzles in our understanding of dark matter. Another hidden aspect of the universe is the intergalactic medium, the gas that fills the space between galaxies. This gas is extremely diffuse, with densities far lower than the best vacuum we can create on Earth. But it exists in such vast volumes that it contains a significant fraction of the universe's normal matter. Most of this gas is hydrogen, with some helium and trace amounts of heavier elements. It is mostly ionized, meaning the electrons have been stripped from the atoms by the intense radiation from stars and quasars. The intergalactic medium is difficult to observe directly because it is so diffuse and faint, but it can be detected through absorption lines in the spectra of distant quasars. When light from a quasar passes through the intergalactic medium, hydrogen atoms absorb specific wavelengths, creating a forest of absorption lines in the quasar's spectrum. By analyzing these lines, astronomers can map the distribution and properties of the intergalactic medium. They can measure its density, temperature, and chemical composition. This provides insights into the history of the universe and the processes that have enriched space with heavy elements. The intergalactic medium also plays a role in the formation and evolution of galaxies. It is the reservoir from which galaxies draw gas to form new stars. As the universe expands and cools, gas in the intergalactic medium can cool and condense, falling into galaxies along filaments of the cosmic web. This infall of gas sustains star formation over billions of years. Without it, galaxies would quickly use up their gas and stop forming stars. But the intergalactic medium is also affected by feedback from galaxies. When massive stars explode as supernovae, they eject gas and energy into the surrounding medium. This can heat the intergalactic medium and enrich it with heavy elements produced in the stars. Supermassive black holes in the centers of galaxies can also drive powerful outflows that push gas into the intergalactic medium. These feedback processes regulate the cycle of gas between galaxies and the intergalactic medium, influencing the rate of star formation and the growth of galaxies. The hidden architecture of the universe also includes structures in time as well as space. The universe has a history that stretches back nearly 14 billion years. At different times in this history, the universe looked very different. In the early universe, galaxies were smaller and more irregular. Star formation was more vigorous. Quasars were more common. As time passed, galaxies grew through mergers and gas accretion. Star formation gradually declined. The universe became quieter and more organized. This cosmic history is recorded in the light we receive from distant objects. Because light takes time to travel, when we look at distant galaxies, we see them as they were in the past. The farther away a galaxy is, the farther back in time we are seeing. By observing galaxies at different distances, astronomers can study how galaxies have evolved over cosmic time. They can see how star formation rates have changed, how galaxy morphologies have evolved, and how the chemical composition of galaxies has been enriched with heavy elements. The most distant galaxies we can see are among the first to have formed. They exist at a time when the universe was less than 1 billion years old. These galaxies are small and faint, often irregular in shape. They are forming stars at prodigious rates, converting gas into stars much faster than galaxies do today. Studying these early galaxies helps us understand how galaxies began and how they grew over time. Between the first galaxies and the present day lies a vast stretch of cosmic history. During this time, the universe underwent significant changes. The first stars formed and died, enriching space with heavy elements. The first black holes grew into supermassive black holes. Galaxies merged and interacted, building up the large galaxies we see today. The cosmic web took shape, with matter flowing along filaments and gathering in clusters. All of this happened in silence, driven by gravity and the expansion of space. One of the most important transitions in cosmic history was the epoch of reionization. In the early universe, after the cosmic microwave background was emitted, the universe entered a period known as the Dark Ages. During this time, the universe was filled with neutral hydrogen gas. There were no stars yet, so there was no light except the fading glow of the cosmic microwave background. The universe was dark and cold. Then the first stars formed. These stars were massive and hot, emitting intense ultraviolet radiation. This radiation ionized the surrounding hydrogen, stripping the electrons from the atoms. Each star created a bubble of ionized gas around itself. As more stars formed, these bubbles grew and began to overlap. Eventually, the entire universe became reionized. Hydrogen went from being neutral to being ionized, just as it is today. This transition, the epoch of reionization, marks the end of the Dark Ages and the beginning of the universe as we know it. The epoch of reionization is difficult to study because it occurred when the universe was very young, and the light from that time is extremely red-shifted and faint. But astronomers are making progress. They are using powerful telescopes to observe the most distant galaxies and to study the intergalactic medium at early times. They are looking for the signature of reionization in the cosmic microwave background and in the spectra of distant quasars. These observations are building a picture of how reionization unfolded and what role the first stars and galaxies played in this process. The hidden architecture of the universe also includes the structure of space-time itself. According to general relativity, space-time is not a fixed stage on which events occur. It is a dynamic entity that can bend and warp in response to matter and energy. Massive objects create curves in space-time. Other objects moving through space-time follow these curves, which we perceive as the force of gravity. On the largest scales, the expansion of the universe is a stretching of space-time itself. As space-time expands, distances between galaxies increase. But the galaxies themselves are not moving through space in the usual sense. They are simply being carried along by the expansion of space-time. This expansion is happening everywhere, at every point in space. It is not an expansion into something. It is an expansion of the fabric of space itself. This expansion can do things that ordinary motion cannot. For example, galaxies can recede from us faster than the speed of light because of the expansion of space. This does not violate relativity, which states that nothing can move through space faster than light, but space itself can expand at any rate. Distant galaxies are receding from us faster than light because the space between us and them is expanding so rapidly. The light from these galaxies is also being stretched by the expansion, shifting it to longer, redder wavelengths. This is called cosmological redshift. The structure of space-time can also be affected by gravitational waves. These are ripples in space-time caused by accelerating masses. When two black holes orbit each other, they create gravitational waves that spread outward at the speed of light. As the black holes spiral closer together, the gravitational waves become stronger and more frequent. When the black holes finally merge, they release a burst of gravitational waves so powerful that it can be detected across the universe. Gravitational waves carry information about the events that created them. By detecting and analyzing gravitational waves, astronomers can learn about the masses, spins and distances of merging black holes and neutron stars. They can test the predictions of general relativity in extreme conditions. They can study populations of compact objects and how they form and evolve. Gravitational wave astronomy is a new window into the universe, revealing phenomena that are invisible in electromagnetic radiation. The hidden architecture of the universe extends to the quantum realm as well. Quantum mechanics governs the behavior of particles at the smallest scales. It introduces uncertainty and probability into the fundamental workings of nature. Even empty space is not truly empty at the quantum level. It is filled with fluctuating fields and virtual particles that pop into and out of existence. These quantum fluctuations may have played a crucial role in the early universe, seeding the density variations that grew into the cosmic web. During the period of cosmic inflation, a brief but dramatic expansion in the first moments after the Big Bang, quantum fluctuations were stretched to macroscopic scales. These fluctuations became the variations in density that we see in the cosmic microwave background. They are the seeds of all structure in the universe. Galaxies, clusters, filaments, and voids all trace their origins back to quantum fluctuations in the first fraction of a second after the Big Bang. The connection between the quantum realm and the cosmic scale is one of the most profound insights in modern cosmology. The hidden architecture of the universe is vast and complex. It includes dark matter and dark energy, the cosmic web, the intergalactic medium, the structure of space-time, and the quantum foundations of reality. All of these components are invisible or silent in one way or another. We cannot see dark matter or dark energy. We cannot hear gravitational waves with our ears. We cannot directly observe the intergalactic medium or quantum fluctuations, but we can infer their existence and study their properties through careful observation and reasoning. This hidden architecture shapes everything we see. It determines how galaxies form and evolve. It governs the expansion of the universe. It influences the distribution of matter on all scales. It connects the smallest quantum fluctuations to the largest structures in the cosmos. Understanding this architecture is one of the great challenges of modern science, and it is a challenge we are meeting with increasingly sophisticated tools and methods. Telescopes in space and on the ground are mapping the universe with unprecedented detail. Gravitational wave detectors are listening to the vibrations of space-time. Particle detectors are searching for dark matter particles. Computer simulations are recreating the formation and evolution of cosmic structures. All of these efforts are revealing the hidden architecture of the universe, piece by piece. As we uncover this architecture, we gain a deeper understanding of the cosmos and our place in it. We see that the universe is not a collection of isolated objects, but an interconnected system. Galaxies are linked by filaments of the cosmic web. The expansion of space affects everything equally. Dark matter and dark energy pervade all of existence. We are part of this vast system, connected to it through gravity, through the atoms in our bodies, and through the light we receive from distant stars and galaxies. The silence of space is not a void. It is a canvas on which the universe paints its story. It is a medium through which invisible forces and particles shape reality. It is a reminder that much of what exists is hidden from our immediate senses, but with patience, curiosity, and ingenuity, we can uncover the hidden and understand the silent. In this chapter, we have explored the hidden architecture of the universe. We have seen how the cosmic web connects galaxies across vast distances. We have considered the mysteries of dark matter and dark energy, the invisible components that dominate the cosmos. We have thought about the intergalactic medium, the structure of space-time, and the quantum fluctuations that seeded all structure. And we have reflected on how these hidden elements shape the universe in silence. As we continue, we will turn our attention to other secrets hidden in the silence of space. We will consider the possibility of life beyond Earth and what the silence might tell us about our chances of finding it. We will think about the distant future of the universe and how the silence will evolve as the cosmos ages. And we will continue to explore the profound mysteries that lie hidden in the vast, silent expanse of space. The universe is full of wonders, many of them invisible and silent, but they are there waiting to be discovered, and as we discover them, we come to appreciate the richness and complexity of the cosmos. We see that the universe is far more than the stars we see in the night sky. It is a tapestry of matter and energy, woven together over billions of years, guided by the fundamental forces of nature. And it is a tapestry that we are only beginning to understand. Galaxies themselves are complex ecosystems. They contain billions of stars, vast clouds of gas and dust, supermassive black holes at their centers, and dark matter halos that extend far beyond the visible edges. All of these components interact with each other in intricate ways. Stars form from gas clouds. They live for millions or billions of years, fusing elements in their cores. When they die, they return enriched material to the interstellar medium. This material can be incorporated into new generations of stars and planets. The Milky Way, our home galaxy, is a spiral galaxy with a disk and a central bulge. The disk contains most of the young stars and the active star-forming regions. The bulge contains older stars. Surrounding the entire galaxy is a spherical halo containing old stars and globular clusters, and beyond the visible stars is the dark matter halo, extending hundreds of thousands of light years from the galactic center. The Milky Way is not isolated. It is part of a small group of galaxies called the Local Group. The Local Group contains about 80 galaxies, most of them small dwarf galaxies. The two largest galaxies are the Milky Way and the Andromeda Galaxy. These two galaxies are slowly moving toward each other. In about 4 billion years, they will collide and merge, forming a single larger galaxy. This merger will reshape both galaxies, but it will happen in silence over millions of years. Galaxy mergers are common in the universe. When two galaxies collide, their stars rarely collide because the distances between stars are so vast, but the gravitational interactions between the galaxies can have dramatic effects. The shapes of the galaxies can be distorted. Long tidal tails of stars and gas can be pulled out. The encounter can trigger bursts of star formation as gas clouds collide and compress. Supermassive black holes at the centers of the galaxies can sink toward the center of the merged system and eventually merge themselves. The merger of supermassive black holes is one of the most energetic events in the universe. As the black holes spiral together, they emit gravitational waves. These waves carry away energy, causing the black holes to move closer. The process accelerates until the black holes merge in a final burst of gravitational waves. This merger can release as much energy in gravitational waves as all the stars in a galaxy emit in light over millions of years. Yet it happens in silence, except for the gravitational waves themselves. Within galaxies, there are regions of intense activity. Star-forming regions, also called stellar nurseries, are places where gas and dust are collapsing to form new stars. These regions are often hidden by dust, which absorbs visible light, but they shine brightly in infrared, the heat radiated by warm dust. Infrared telescopes can peer through the dust and reveal the young stars within. These regions are dynamic and complex, with powerful stellar winds and radiation from young stars sculpting the surrounding gas and dust. Some of the most famous star-forming regions include the Orion Nebula, the Eagle Nebula, and the Carina Nebula. These regions are relatively nearby, allowing astronomers to study them in detail. They contain thousands of young stars in various stages of formation. Some stars are still embedded in their birth cocoons of gas and dust. Others have emerged and begun to clear away the surrounding material. The study of these regions helps us understand how stars form and how they affect their environment. Star formation is regulated by a balance of forces. Gravity pulls gas together. Pressure and turbulence resist this compression. Magnetic fields can support gas against collapse. Radiation from young stars can heat and disperse gas. The interplay of these forces determines where and when stars form. In some regions, star formation is vigorous, with many stars forming in a short period. In other regions, star formation is slow and sporadic. Massive stars have a particularly strong influence on their surroundings. They emit intense ultraviolet radiation that ionizes the nearby gas, creating glowing regions called H2 regions. They drive powerful stellar winds that can sweep up and compress surrounding gas. And when they die in supernova explosions, they inject energy and heavy elements into the interstellar medium. These processes can trigger new waves of star formation or can suppress star formation by dispersing gas. The life cycle of massive stars is intimately connected to the evolution of their host galaxies. Supernovae are not the only way stars can end their lives. Lower mass stars like the Sun evolve more gently. After exhausting the hydrogen in their cores, they swell into red giants. The outer layers of the star expand, cooling and glowing red. The core contracts and heats up, eventually igniting helium fusion. This produces carbon and oxygen in the core. When the helium is exhausted, the core contracts again, but it is not hot enough to fuse carbon. The outer layers are gently expelled, forming a planetary nebula. The core remains as a white dwarf, a dense hot ember that will cool slowly over trillions of years. Planetary nebulae are beautiful and diverse. They come in many shapes: spheres, rings, butterflies, and more. These shapes are sculpted by stellar winds, rotation, and the interaction of material expelled at different times. The central white dwarf illuminates the nebula with ultraviolet light, causing it to glow in various colors. Each element emits light at specific wavelengths, creating a spectrum of colors that reveals the nebula's composition. White dwarfs are the final state for most stars. They are about the size of Earth but contain as much mass as the Sun. Their density is so high that a teaspoon of white dwarf material would weigh several tons. White dwarfs are supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that arises when electrons are packed extremely tightly. They emit light because they are hot, but they have no internal energy source. Over time, they cool and fade, eventually becoming black dwarfs, cold and dark remnants that no longer emit light. Neutron stars are even more extreme. They form when a massive star's core collapses in a supernova. If the core's mass is between about 1.4 and 3 times the mass of the Sun, it collapses into a neutron star. The collapse is so complete that protons and electrons are crushed together, forming neutrons. The result is a star made almost entirely of neutrons, packed so densely that a teaspoon of neutron star material would weigh as much as a mountain. Neutron stars are only about 20 kilometers across. but they contain more mass than the Sun. They spin rapidly, often hundreds of times per second, because the collapse conserves angular momentum. They have incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields channel radiation into beams that sweep across space as the neutron star rotates. If one of these beams happens to point toward Earth, we detect it as a pulsar. Pulsars were first discovered in the 1960s. At first, their regular pulses were so precise that some astronomers jokingly considered whether they might be signals from an alien civilization. But further study revealed their true nature as rotating neutron stars. Pulsars have since become valuable tools for studying the universe. Their precise timing can be used to test theories of gravity, to detect gravitational waves, and to measure distances across the galaxy. Some neutron stars are members of binary systems. If the companion star is massive enough, gas can flow from it onto the neutron star. This gas forms an accretion disk around the neutron star and spirals inward. As it falls onto the neutron star's surface, it releases a tremendous amount of energy, often in the form of X-rays. These X-ray binaries can be extremely bright, outshining entire galaxies in X-rays. They are laboratories for studying matter under extreme conditions. In rare cases, two neutron stars can orbit each other. Over time, they lose energy by emitting gravitational waves and spiral closer together. Eventually, they merge in a cataclysmic event called a kilonova. The merger produces a burst of gravitational waves and a flash of electromagnetic radiation across the spectrum, from gamma rays to radio waves. It also produces heavy elements, including gold and platinum, through a process called rapid neutron capture. The first detection of a neutron star merger in both gravitational waves and light occurred in 2017 and provided strong evidence that kilonovae are a major source of heavy elements in the universe. Black holes represent the ultimate extreme. If a collapsing stellar core is more massive than about 3 solar masses, not even neutron degeneracy pressure can stop the collapse. The core continues to shrink, becoming denser and denser, until it reaches a point of infinite density called a singularity. Around the singularity, there is a boundary called the event horizon. Anything that crosses this boundary is pulled inexorably toward the singularity and cannot escape, not even light. Black holes are defined by a few simple properties: mass, spin, and electric charge. Most black holes are electrically neutral, so they are characterized by just their mass and spin. Despite this simplicity, black holes are among the most fascinating objects in the universe. They warp space-time around them so severely that time slows down near the event horizon. They can grow by accreting matter or by merging with other black holes. And they play a crucial role in the evolution of galaxies. Supermassive black holes, millions to billions of times the mass of the Sun, reside at the centers of most large galaxies. The Milky Way has a supermassive black hole at its center, called Sagittarius A. It has a mass of about 4 million solar masses. We cannot see the black hole itself, but we can observe stars orbiting around it. By tracking the motion of these stars, astronomers have confirmed the presence of the black hole and measured its mass. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. The black hole is at the center of the galaxy M87, about 55 million light-years away. It has a mass of about 6.5 billion solar masses. The image shows a dark region, the shadow of the black hole, surrounded by a bright ring of hot gas. This image confirmed predictions from general relativity and provided a new way to study black holes. Supermassive black holes can have a profound influence on their host galaxies. When gas falls into a supermassive black hole, it forms an accretion disk. The disk heats up and emits radiation. This radiation can be so intense that it outshines all the stars in the galaxy combined. The galaxy is said to host an active galactic nucleus, or AGN. The most luminous AGN are called quasars. Quasars are among the most distant and luminous objects in the universe. They are powered by supermassive black holes accreting gas at tremendous rates. The radiation from quasars can drive powerful winds that clear gas from the galaxy, shutting down star formation. This feedback process is thought to regulate the growth of galaxies and black holes, keeping them in balance. Without this feedback, galaxies would form stars too quickly and would look very different from what we observe. The study of black holes, neutron stars, white dwarfs, and other compact objects reveals the endpoints of stellar evolution. Each star's fate is determined by its mass. Low-mass stars become white dwarfs. High-mass stars explode as supernovae and leave behind neutron stars or black holes. These remnants continue to shape the universe, influencing the interstellar medium, triggering star formation, and contributing to the chemical enrichment of galaxies. All of this activity, from the gentle fading of white dwarfs to the violent mergers of black holes, happens in the silence of space. We detect it through light, through gravitational waves, through neutrinos, but never through sound. The silence is a fundamental feature of the cosmos, a consequence of the vacuum of space, and within that silence, the universe continues its grand processes, indifferent to our presence or absence. The hidden architecture of the universe also includes patterns we are only beginning to understand. For example, there is evidence for a slight asymmetry between matter and antimatter. In the early universe, matter and antimatter should have been created in equal amounts, but if that were the case, they would have annihilated each other, leaving only radiation. Yet our universe is made of matter. There must be some process that created a slight excess of matter over antimatter. This asymmetry is one of the great unsolved problems in physics. Another mystery is the nature of time itself. In our everyday experience, time flows in one direction from past to future. But the fundamental laws of physics are mostly symmetric with respect to time. They work the same way whether time runs forward or backward. The arrow of time, the distinction between past and future, seems to emerge from the second law of thermodynamics, which states that entropy always increases. But why entropy increases and why the universe started in a low entropy state are deep questions that physicists are still grappling with. The hidden architecture also includes the possibility of extra dimensions. In our everyday experience, space has 3 dimensions: length, width, and height. Time is sometimes considered a 4th dimension, but some theories of physics, such as string theory, propose that there may be additional spatial dimensions beyond the 3 we perceive. These extra dimensions could be compactified, curled up so small that we cannot detect them. Or they could exist in some other form that is not directly accessible to us. The existence of extra dimensions could have profound implications for our understanding of gravity, quantum mechanics, and the fundamental structure of reality. All of these mysteries are hidden in the silence of space. They do not announce themselves. They must be inferred from subtle observations and careful reasoning. They require patience, creativity, and a willingness to question our assumptions. And they remind us that the universe is far stranger and more wonderful than we might have imagined. As we explore the hidden architecture of the universe, we also develop new technologies and methods. We build more sensitive detectors. We launch more powerful telescopes. We develop better algorithms for analyzing data. We create more sophisticated simulations. Each advancement brings us closer to understanding the universe's secrets. And each discovery raises new questions, driving us forward in an endless cycle of inquiry. The silence of space is not an obstacle, it is an invitation. It invites us to look beyond the obvious, to listen for signals that are faint or unfamiliar, to imagine possibilities that we have not yet considered. It challenges us to expand our perspective, to think on cosmic scales, to appreciate the vastness and complexity of existence. In this chapter, we have delved into the hidden architecture of the universe. We have explored the cosmic web, the distribution of dark matter and dark energy, the intergalactic medium, and the structure of space-time. We have considered the life cycles of stars, the formation of compact objects, and the role of supermassive black holes. We have touched on mysteries like the matter-antimatter asymmetry and the arrow of time. And throughout, we have seen how the silence of space both hides and reveals, concealing details from our immediate senses, but allowing us to uncover them through observation and thought. As we move forward, we will continue to explore what the silence is hiding. We will turn our attention to the search for life beyond Earth, considering what the silence might tell us about the prevalence of life in the universe. We will think about the far future, imagining how the universe will evolve over trillions of years, and we will reflect on the meaning of our existence in this vast, silent cosmos, contemplating our place in the grand sweep of cosmic history. In all the vastness of space, in all the silence that surrounds us, one question stands out above many others. Are we alone? This question has haunted humanity for as long as we have looked up at the stars. It is a question that touches on our deepest hopes and fears, and it is a question that the silence of space seems to answer, though not in the way we might wish. When we search for life beyond Earth, we are searching for something that might break the silence. We are listening for signals, looking for signs, hoping to find evidence that somewhere out there, other beings exist, other minds, other civilizations, but so far the silence remains unbroken. The universe seems empty of voices other than our own. This silence is puzzling. The universe is vast beyond comprehension. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. Some of those planets are similar to Earth, with liquid water on their surfaces and atmospheres that might support life. The numbers suggest that life should be common, yet we see no evidence of it. This contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The Fermi paradox forces us to confront several possibilities. Perhaps life is extraordinarily rare. Perhaps the conditions needed for life to arise are so specific that Earth is one of only a handful of worlds where it has happened. Or perhaps life is common, but intelligent life is rare. The step from simple microbes to complex technological civilizations might be so difficult that it happens only once in billions of years, on only a few worlds in each galaxy. Another possibility is that intelligent civilizations exist, but they do not last long. Technology brings risks: nuclear weapons, environmental destruction, artificial intelligence, bioengineered pathogens. These and other dangers might destroy civilizations soon after they develop the ability to communicate across interstellar distances. If civilizations typically last only a few centuries after reaching this stage, then at any given time, very few civilizations would be active. The galaxy might have been home to thousands or millions of civilizations over its history, but most of them are now extinct. The silence would be a graveyard silence, the quiet of worlds that once spoke but speak no more. Or perhaps civilizations exist, but choose not to communicate. They might be aware of the risks of revealing themselves. Broadcasting your presence to the galaxy could attract unwanted attention from hostile civilizations. It might be safer to remain silent, to listen, but not speak. This is sometimes called the dark forest hypothesis, the idea that the galaxy is like a dark forest where every civilization hides, knowing that revealing yourself could be fatal. There is also the possibility that civilizations exist but are so different from us that we do not recognize their signals. We search for radio transmissions because that is how we communicate, but an advanced civilization might use technologies we have not imagined. They might communicate through methods that are invisible to our current instruments, or they might not feel the need to communicate at all, having transcended the desire for contact with other species. Each of these possibilities has implications for what the silence is hiding. If life is rare, then the silence hides the emptiness of a universe where biology is an anomaly, a rare accident that happens only under the most precise conditions. If intelligent life is rare, then the silence hides billions of worlds teeming with microbes and simple organisms, but very few worlds where those organisms have evolved into beings capable of contemplation and communication. If civilizations are short-lived, then the silence hides the ruins of countless societies, the remnants of cultures that once looked up at their own night skies and wondered the same questions we wonder. If civilizations are hiding, then the silence is an illusion, a facade behind which countless intelligences watch and wait, perhaps aware of us but choosing not to respond. And if civilizations are simply beyond our understanding, then the silence hides forms of life and intelligence so alien that we cannot even conceive of them. To understand these possibilities, we must first understand what we know about life. Life on Earth is built from a few basic ingredients: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These elements combine to form complex molecules like proteins, nucleic acids, and lipids. These molecules self-organize into cells. Cells reproduce, passing information from one generation to the next through DNA. Over time, random mutations and natural selection lead to the evolution of more complex forms. This process took billions of years on Earth. Life arose relatively quickly after the planet formed, within the first billion years. For most of Earth's history, life consisted only of single-celled organisms. It took about 3 billion years for multicellular life to evolve. Complex organisms, like plants and animals, appeared only in the last half-billion years. Humans have existed for only a few 100,000 years, a tiny fraction of Earth's history. The fact that life arose quickly on Earth suggests that the transition from chemistry to biology might not be as difficult as once thought. If the right conditions exist, life might emerge readily. But the fact that complex life took so long to evolve suggests that the path from simple cells to complex organisms is difficult. There may be many planets with microbes, but far fewer with animals, plants, or intelligent beings. What are the right conditions for life? On Earth, life requires liquid water, a source of energy, and the right chemical ingredients. Water is essential because it is a versatile solvent that allows complex chemistry to occur. Energy is needed to drive the chemical reactions that sustain life, and the right elements must be available to build the molecules of life. Many exoplanets, planets orbiting other stars, have been discovered in recent years. Thousands are now known. Some of these planets orbit in the habitable zone of their stars, the region where temperatures allow liquid water to exist on the surface. These planets are potential homes for life, but being in the habitable zone does not guarantee that a planet has life. It only means that the conditions might be right. To determine whether a planet actually has life, we need to study its atmosphere. Life affects the composition of a planet's atmosphere. On Earth, oxygen makes up about 20% of the atmosphere. This oxygen is produced by photosynthetic organisms, primarily plants and cyanobacteria. Without life continuously producing oxygen, chemical reactions would remove it from the atmosphere in a relatively short time. The presence of large amounts of oxygen, along with other gases like methane, could be a sign of life. Detecting these gases in the atmospheres of distant planets is challenging. When a planet passes in front of its star, some of the star's light passes through the planet's atmosphere. Different gases absorb light at different wavelengths. By analyzing the spectrum of light that passes through the atmosphere, astronomers can determine which gases are present. This technique, called transmission spectroscopy, has been used to study the atmospheres of several exoplanets. So far, no definitive signs of life have been found, but the search is ongoing. Even if we find biosignatures, gases that suggest the presence of life, we must be careful. Not all biosignatures are definitive. Oxygen can be produced by non-biological processes, such as the breakdown of water molecules by ultraviolet light. Methane can be produced by geological activity. To be confident that we have detected life, we would need to find multiple gases in combinations that are difficult to explain without biology. We would need to rule out alternative explanations, and we would need to confirm our findings with independent observations. The search for life is not limited to distant exoplanets. Within our own solar system, there are several worlds that might harbor life. Mars is the most obvious candidate. It is cold and dry today, but there is evidence that it once had liquid water on its surface. Ancient riverbeds, lake beds, and minerals that form in water suggest that Mars had a warmer, wetter climate billions of years ago. If life arose on Mars during that time, it might still exist today, perhaps underground where liquid water could persist. Several spacecraft have explored Mars, searching for signs of past or present life. The Viking landers in the 1970s conducted experiments designed to detect microbial life in the Martian soil. The results were intriguing but ambiguous. More recent missions have focused on understanding Mars's history and identifying locations where life might have existed. The Perseverance rover, currently exploring Mars, is collecting samples that will eventually be returned to Earth for detailed analysis. These samples could provide the first definitive evidence of life beyond Earth. Beyond Mars, the icy moons of the outer solar system are also promising targets. Europa, a moon of Jupiter, has a surface covered in ice, but beneath that ice lies a vast ocean of liquid water. The ocean is kept warm by tidal heating, the friction generated as Europa is stretched and squeezed by Jupiter's gravity. This ocean could have all the ingredients needed for life: water, energy, and chemical nutrients. Similar oceans likely exist on other moons, including Enceladus, a moon of Saturn, and possibly Ganymede and Callisto, two other moons of Jupiter. Enceladus has been observed ejecting plumes of water vapor and ice particles from cracks in its surface. These plumes come from the subsurface ocean and contain organic molecules, the building blocks of life. A spacecraft could fly through these plumes and analyze their composition, searching for signs of life without even needing to land. Missions to Europa and Enceladus are being planned, with the goal of determining whether these moons harbor life. Even if we find microbial life in our solar system, it would not answer the question of whether intelligent life exists elsewhere. Microbes do not build radio telescopes or send signals into space. To find intelligent life, we must look beyond our solar system, searching for signs of technology. The search for extraterrestrial intelligence, known as SETI, has been ongoing for more than 60 years. It began in earnest in 1960, when astronomer Frank Drake used a radio telescope to listen for signals from two nearby stars. He detected nothing. Since then, SETI searches have become more sophisticated, scanning millions of stars across a wide range of frequencies. But still, nothing has been detected. The silence remains. SETI searches typically focus on radio waves because they travel well through space and are relatively easy to generate and detect. A civilization wishing to communicate might send a strong, narrow-band signal at a frequency that stands out from natural sources. Alternatively, they might send a broadband signal containing information, like the signals we use for communication on Earth. SETI searches look for both types of signals. One challenge is knowing where to look. The galaxy is vast, with hundreds of billions of stars. Even with powerful telescopes, we can only search a tiny fraction of the sky at any given time. We must make guesses about which stars are most likely to host intelligent life and focus our searches there. We tend to prioritize stars similar to the Sun, as these are thought to be good candidates for having habitable planets. Another challenge is knowing when to look. If civilizations are short-lived, then the window of time during which they are broadcasting signals might be brief. We could be searching at the wrong time, listening to stars where civilizations existed millions of years ago or will exist millions of years in the future. The timing must align for us to detect a signal. There is also the question of whether advanced civilizations would bother with radio signals at all. Radio communication is effective over interstellar distances, but it is slow. A message sent to a star 10 light-years away would take 10 years to arrive. A reply would take another 10 years to return. This makes conversation impossible. An advanced civilization might prefer other methods of communication, or they might have abandoned active communication altogether, relying instead on passive observation or technologies we have not yet imagined. Despite these challenges, SETI searches continue. New telescopes and techniques are being developed. The Square Kilometre Array, currently under construction, will be the most sensitive radio telescope ever built. It will be able to detect signals from civilizations thousands of light-years away. The search is also expanding beyond radio waves. Some projects are looking for optical signals, brief flashes of laser light that a civilization might use to communicate. Others are searching for techno-signatures, signs of advanced technology such as artificial structures around stars or the waste heat from massive energy use. One of the most famous potential signals detected by SETI was the WOW signal in 1977. It was a strong, narrow-band radio signal detected by the Big Ear telescope in Ohio. The signal lasted for 72 seconds and came from the direction of the constellation Sagittarius. It was so unusual that the astronomer who discovered it wrote "WOW" in the margin of the printout. Despite numerous attempts, the signal was never detected again. Its origin remains a mystery. It could have been a natural phenomenon, a glitch in the equipment, or possibly a signal from an extraterrestrial civilization. We will likely never know. The absence of detected signals is itself a kind of data. It tells us something about the prevalence of intelligent civilizations, or at least about their communication habits. If the galaxy were teeming with civilizations, all broadcasting their presence, we would expect to have detected something by now. The silence suggests that such civilizations are either rare or quiet, or using communication methods we are not monitoring. Some scientists have turned the question around. Instead of just listening, should we be broadcasting? Should we send signals into space, announcing our presence and inviting a response? This idea, known as active SETI or METI, messaging to extraterrestrial intelligence, is controversial. Some argue that it is premature and potentially dangerous. We do not know what is out there. Broadcasting our location could attract unwanted attention. Others argue that any civilization capable of traveling to Earth would have already detected us through the radio and television signals we have been inadvertently broadcasting for decades. In either case, the decision to actively signal our presence is a profound one, with implications for all of humanity. Even if we never detect a signal, the search for life beyond Earth continues through other means. The study of exoplanets is revealing the diversity of worlds in the galaxy. We have found planets orbiting close to their stars, so hot that their surfaces are molten. We have found planets far from their stars, frozen and dark. We have found gas giants larger than Jupiter and rocky planets smaller than Earth. We have found planets orbiting binary stars, planets with eccentric orbits, and planets in systems very different from our own solar system. This diversity tells us that planet formation is a robust process. Planets form in many different environments under many different conditions. If planets are common, then the building blocks of life are also likely common. The elements needed for life are produced in stars and distributed through space by supernova explosions. Water is abundant in the form of ice in the outer regions of planetary systems. Organic molecules, the building blocks of life, have been detected in interstellar clouds and in comets. The ingredients are there. The question is whether they come together in the right way to produce life. The study of life on Earth provides some clues. Life on Earth is remarkably resilient. It exists in almost every environment imaginable. Microbes have been found in the deepest oceans, in boiling hot springs, in frozen Antarctic ice, in acidic lakes, and in the dry deserts. Life can survive extreme temperatures, extreme pressures, high radiation, and complete darkness. This adaptability suggests that life might be able to exist in a wide range of environments beyond Earth. Extremophiles, organisms that thrive in extreme conditions, expand our understanding of where life might exist. If life can survive in the harsh conditions found in some places on Earth, it might also survive in the harsh conditions on other worlds. The subsurface oceans of icy moons, the acidic clouds of Venus, the frozen soil of Mars, all of these environments might be habitable for extremophiles. There is also the possibility of life based on different chemistry. All life on Earth uses water as a solvent and carbon as the basis for complex molecules. But in theory, life could use other solvents such as ammonia or methane, and other elements such as silicon as the basis for its biochemistry. Such life would be very different from life on Earth, with different requirements and different signatures. It might be harder to detect because we would not know what to look for. The search for life is also a search for understanding ourselves. If we find that life is common in the universe, it would suggest that the processes that led to life on Earth are not unique. It would mean that we are part of a larger story, one that plays out on countless worlds. It would change our perspective on our place in the cosmos. We would no longer be alone, but part of a vast community of living worlds. On the other hand, if we find that life is rare, or that we are the only intelligent civilization in the galaxy, it would also be profound. It would mean that we are precious, a rare flowering of complexity in a universe that is mostly barren. It would place a greater responsibility on us to preserve and cherish the life that exists on Earth, knowing that it might be the only life anywhere nearby. The silence of space does not give us easy answers. It forces us to grapple with uncertainty. It challenges us to keep searching, even when we find nothing. It requires patience and humility. We must accept that we may not find what we are looking for in our lifetimes, or even in the lifetimes of many generations to come. But the search is worthwhile because the question is important. There is also the question of what we would do if we did detect a signal. How would we respond? Who would speak for humanity? What would we say? These are not easy questions. They require international cooperation and careful thought. A detection would be one of the most significant events in human history. It would unite us in a shared sense of wonder and curiosity. It might also divide us as different groups and nations debated how to respond. Protocols have been developed for what to do if a signal is detected. The first step would be to verify the signal, ensuring that it is not a mistake or a hoax. Multiple observatories would be asked to confirm the detection. Once confirmed, the information would be shared with the scientific community and eventually with the public. The decision of how to respond, if at all, would be made through international consultation. It would not be a decision for any one person or nation to make alone. The silence of space is also a reminder of the vastness of time. Even if civilizations are common, the chances of two civilizations existing at the same time and being close enough to communicate are small. The universe is nearly 14 billion years old. Human civilization has existed for only a few thousand years. We have been capable of sending and receiving radio signals for only about a century. In the cosmic timeline, this is the blink of an eye. A civilization on the other side of the galaxy might have flourished a billion years ago, long before Earth even formed. Another civilization might arise a billion years from now, long after humanity has gone extinct. The silence we experience might simply be a consequence of timing. We might be listening at the wrong moment in cosmic history. This perspective can be both humbling and comforting. It reminds us that we are part of a process that is much larger and longer than our individual lives or even our species. The universe has been here for eons before us and will continue for eons after us. We are participants in a grand experiment, the experiment of complexity and consciousness emerging from matter and energy. The search for life also drives technological innovation. The telescopes, instruments, and techniques developed for astrobiology and SETI have applications beyond the search for extraterrestrial life. They advance our understanding of planetary science, atmospheric chemistry, and the formation of stars and planets. They improve our ability to detect faint signals and analyze complex data. These advances benefit many areas of science and technology. The question of life beyond Earth also raises philosophical and ethical questions. If we find life, especially intelligent life, how should we interact with it? Do we have a responsibility to protect it? Should we try to communicate, or should we observe from a distance? These questions touch on issues of ethics, anthropology, and our understanding of what it means to be alive and conscious. There is also the question of whether we should try to preserve life on Earth in the event of a catastrophe. Some scientists have proposed creating backups of Earth's biosphere, storing genetic information and samples in secure locations, either on Earth or in space. This would ensure that if something happened to Earth, the information needed to recreate life could be preserved. Others have proposed sending probes to other star systems, carrying the seeds of life, so that even if Earth is destroyed, life could continue elsewhere. These ideas are speculative, but they reflect a deep concern for the continuation of life, not just human life, but all life. The silence of space might also be hiding something more subtle. Perhaps the universe is filled with life, but it is life that we would not recognize as such. Perhaps there are forms of consciousness that do not rely on biology, but on other substrates. Some scientists and philosophers have speculated about the possibility of machine intelligence, artificial minds that could arise from advanced technology. Such minds might be very different from biological minds, with different goals, different values, and different ways of experiencing the universe. If machine intelligence exists, it might be very hard to detect. It might not broadcast radio signals or build structures that we would recognize. It might operate on timescales that are very different from ours, thinking much faster or much slower. It might not be interested in communicating with biological civilizations like ours. The silence could be hiding a universe populated by machine minds, indifferent to the biological organisms that gave rise to them. There is also the possibility of life existing in forms we have not yet imagined. Life on Earth is carbon-based, but carbon is not the only element that can form complex molecules. Silicon can also form chains and rings, though it is less versatile than carbon. In environments where carbon is scarce but silicon is abundant, silicon-based life might be possible. Such life would be very different from anything on Earth. Plasma-based life has also been speculated about. Plasma is a state of matter where atoms are ionized, with electrons separated from nuclei. Plasma can form complex, self-organizing structures under certain conditions. Some scientists have proposed that these structures could, in principle, exhibit lifelike behavior, including reproduction and evolution. Such life would exist in environments like the atmospheres of stars or the interstellar medium, far from the rocky planets we typically associate with life. These speculative forms of life remind us that our understanding is limited by our experience. We only know one example of life on Earth. We use this example as a template for what we search for. But the universe might be far more creative than we can imagine. The silence might be hiding forms of life that are so different from us that we would not recognize them even if we encountered them. The question of other voices in the silence is not just a scientific question. It is also a deeply human question. We are social beings. We thrive on connection and communication. The idea that we might be alone in the universe is both terrifying and lonely. It suggests a cosmos that is indifferent to us, a vast stage with only one actor. But the idea that we are not alone, that somewhere out there other minds exist, is both exhilarating and humbling. It suggests that we are part of something larger, a community of conscious beings scattered across the stars. Whether we are alone or not, the search itself has value. It pushes us to explore, to question, to reach beyond our current limits. It inspires us to develop new technologies and new ways of thinking. It brings us together in a shared endeavor, transcending national and cultural boundaries, and it reminds us of our place in the cosmos, small and fragile, yet capable of contemplating the infinite. As we continue to search, we must also reflect on what we have learned. The silence has taught us patience. It has taught us humility. It has taught us that the universe does not owe us answers. It simply is. And it is up to us to ask the questions, to seek the evidence, to piece together the story of the cosmos and our place in it. The silence of space might be hiding other voices, other minds, other forms of life, or it might simply be revealing the truth that we are for now alone. Either way, the silence invites us to listen more carefully, to look more closely, to think more deeply. It challenges us to imagine possibilities beyond our current understanding. And it reminds us that the greatest discoveries often come not from finding what we expect, but from confronting what we do not. In our solar system, the search for life continues with renewed vigor. Future missions to Mars will drill deeper into the surface, searching for signs of ancient or present life. Missions to Europa and Enceladus will study their subsurface oceans, looking for the chemical signatures of biology. Telescopes in space and on the ground will continue to study exoplanets, refining our ability to detect biosignatures in their atmospheres. And SETI will keep listening, scanning the sky for signals that might indicate the presence of intelligent life. Each of these efforts is a piece of a larger puzzle. Together they form a comprehensive approach to answering one of the most profound questions we can ask. And even if the answer eludes us for generations, the search itself enriches our understanding of the universe and our place within it. The silence of space is profound. It is a silence that spans billions of light years and billions of years of time. It is a silence that has witnessed the birth and death of countless stars, the formation and dissolution of galaxies, the rise and fall of who knows how many worlds. Within that silence, we are a single voice calling out into the dark, hoping for an answer. So far, the silence has not replied, but we continue to call. We continue to listen. We continue to search, because the question matters, because the search itself is part of what makes us human, and because somewhere in the vastness of space, hidden in the silence, there might be something huge, something wonderful, something that will change everything we thought we knew. As we contemplate the possibility of life beyond Earth, we must also consider what this means for our own future. If life is common, then the universe is full of potential. There might be countless worlds where evolution has taken different paths, producing different forms of life, different intelligences, different civilizations. The diversity would be staggering. Each world would have its own story, its own history, its own unique contribution to the cosmic narrative. If intelligent life is common, then the future might hold encounters with other civilizations. These encounters could be peaceful and mutually beneficial, leading to an exchange of knowledge and culture. Or they could be challenging, as civilizations with different values and goals come into contact. Science fiction has explored many possibilities, from benevolent aliens sharing their wisdom to hostile invaders seeking to conquer. The reality, if we ever encounter it, will likely be stranger and more nuanced than fiction can capture. But even if we never encounter another civilization, the search itself has value. It teaches us about the universe and about ourselves. It pushes the boundaries of our knowledge and our technology. It inspires wonder and curiosity. And it reminds us that we are part of something much larger than ourselves, connected to the cosmos through the atoms in our bodies and the light we receive from distant stars. The silence also invites us to consider our responsibilities. If we are alone, or if intelligent life is very rare, then we have a duty to preserve and protect the life that exists on Earth. We are the custodians of a rare and precious phenomenon. The choices we make today will determine whether life on Earth continues to flourish or whether it is diminished or destroyed. This is a heavy responsibility, but also a profound opportunity. We have the chance to shape the future, not just for our own species, but for all the life that shares this planet with us. If we are not alone, if other civilizations exist, then we also have a responsibility to represent our species well. How we conduct ourselves, how we treat each other and our planet, might be observed by others. We would want to be a civilization that is worthy of contact, one that has overcome its divisions and its destructive tendencies, one that has learned to live sustainably and peacefully. The search for extraterrestrial life is also a mirror, reflecting back on us and asking us to consider what kind of species we want to be. The silence of space does not provide easy answers to these questions. It does not tell us whether we are alone or whether we have neighbors among the stars. It does not tell us what the future holds or what our responsibilities are, but it does provide a context, a vast and ancient stage on which our story unfolds, and it invites us to think deeply about that story, about where we have come from, where we are going, and what we hope to find along the way. As we search for life in the universe, we are also discovering more about the conditions that make life possible. We are learning which types of stars are most likely to host habitable planets. We are understanding the role of planetary atmospheres, magnetic fields, and geological activity in creating and maintaining habitable conditions. We are studying how life adapts to different environments and how it might arise from non-living chemistry. One important factor is the presence of liquid water. Water is essential for life as we know it. It is a universal solvent, allowing a wide range of chemical reactions to occur. It remains liquid over a relatively wide temperature range, and it expands when it freezes, which helps protect aquatic life during cold periods. Finding liquid water on other worlds is a high priority in the search for life. Another important factor is the presence of an atmosphere. Atmospheres protect planets from harmful radiation and help regulate temperature. They can provide the gases needed for life, such as oxygen and carbon dioxide. They can transport heat and moisture, creating diverse climates and weather patterns. Understanding planetary atmospheres is crucial for assessing habitability. Magnetic fields also play a role. A planet's magnetic field can shield it from the solar wind, the stream of charged particles emitted by its star. Without this protection, the solar wind can strip away a planet's atmosphere over time. Mars, for example, lost much of its atmosphere billions of years ago, partly because its magnetic field weakened and could no longer protect it. Understanding planetary magnetic fields helps us identify which worlds are most likely to retain their atmospheres and remain habitable over long periods. Geological activity is another factor. Plate tectonics, volcanism, and other geological processes recycle nutrients and regulate atmospheric composition. On Earth, the carbon cycle, driven by geological activity, helps maintain stable temperatures over geological time. Worlds without geological activity might become lifeless as their atmospheres and surfaces become chemically stagnant. All of these factors interact in complex ways. A planet must be the right distance from its star. With the right size and composition, the right atmosphere, the right magnetic field, and the right level of geological activity. The combination of conditions must be just right, a delicate balance that allows life to emerge and persist. Finding worlds with all these conditions is challenging, but not impossible, and each discovery brings us closer to answering the question of whether life exists beyond Earth. The study of Earth's own history also provides insights. Life on Earth has survived multiple mass extinctions, events where a large fraction of species went extinct in a relatively short time. The most famous is the extinction that wiped out the dinosaurs 66 million years ago, caused by an asteroid impact. But there have been others, some even more severe. The Permian-Triassic extinction, about 250 million years ago, killed more than 90% of marine species and 70% of terrestrial species, yet life survived and eventually diversified again. These mass extinctions show that life is resilient but also vulnerable. A single catastrophic event can dramatically alter the course of evolution. If similar events occur on other worlds, they could prevent the development of complex life or intelligent civilizations. Or they could create opportunities, clearing the way for new forms of life to evolve and diversify. The history of life on Earth is a history of both continuity and change, stability and catastrophe. Understanding this history helps us appreciate the fragility and resilience of life. It also helps us understand the challenges that any civilization faces: natural disasters, climate change, resource depletion, disease. These are challenges that any technological civilization might encounter. How they respond to these challenges determines whether they survive and thrive or decline and go extinct. The silence of space might reflect the difficulty of this challenge, the fact that many civilizations might fail to navigate it successfully. There is also the question of what happens to a civilization after it reaches a certain level of technological advancement. Some futurists speculate that advanced civilizations might undergo a transition, moving beyond biological forms and merging with their technology. They might upload their consciousnesses into machines, becoming digital entities. They might engineer themselves, enhancing their biology with technology. Or they might create artificial intelligences that surpass them and take over their role as the dominant intelligence. If such transitions are common, then advanced civilizations might not look anything like we expect. They might not build radio telescopes or send signals into space. They might retreat into virtual realities, exploring universes of their own creation. They might focus on internal development rather than external exploration. The silence could be hiding civilizations that have turned inward, content to exist in their own simulated worlds, indifferent to the physical universe around them. These speculations highlight how much we do not know. We are making guesses based on limited information, extrapolating from our own experience and our own assumptions. The reality could be very different. The universe might be far stranger than we can imagine, and the silence might be hiding things that we have not yet thought to consider. But speculation is not idle. It drives the search forward. It helps us think about what to look for and where to look for it. It expands our perspective, allowing us to consider possibilities beyond the obvious. And it reminds us that the universe is a place of endless variety and surprise, where the unexpected is often the norm. As we continue our search, we are also becoming more aware of the ethical dimensions. If we find life, especially intelligent life, we will face difficult questions. Do we have the right to study it, to interfere with it, to contact it? What if our contact causes harm, either intentionally or unintentionally? What if the life we find is very different from us, with values and experiences we cannot understand? How do we navigate these ethical challenges? These are not hypothetical questions. They are questions we will need to answer if we ever make contact. And they are questions we should think about now, before the moment arrives. Developing ethical frameworks for contact with extraterrestrial life is an important part of preparing for the future. It requires input from many disciplines: science, philosophy, ethics, law, anthropology, and more. It requires international cooperation and careful thought. The silence of space gives us time to prepare. It allows us to think through these issues before we are confronted with them. It is a gift, in a way, a period of reflection before the moment of encounter. And it challenges us to become the kind of species that is ready for contact, one that has thought deeply about its values and its responsibilities. In the meantime, the search continues. Telescopes scan the sky. Spacecraft explore our solar system. Scientists analyze data, looking for patterns and anomalies. The silence persists, but it is not discouraging. It is simply a fact, a condition of the universe as we currently understand it. And it is a condition that might change at any moment. A single detection, a single confirmed signal, could transform our understanding of the cosmos and our place in it. The search for life is also a search for meaning. Humans have always sought to understand their place in the universe. We have asked where we come from, why we are here, and whether we are alone. These questions are fundamental to our existence. They shape our worldview and our sense of purpose. Finding life beyond Earth would provide new answers to these questions, or at least new perspectives on them. It would show us that life is not unique to Earth, that the processes that created us are part of a larger pattern. It would connect us to the cosmos in a profound way. Even if we do not find life, the search itself has meaning. It is an expression of our curiosity, our desire to explore and understand. It is a testament to our ability to ask questions that transcend our immediate needs and concerns. It is a reminder that we are more than just survival machines. We are beings capable of wonder, of awe, of contemplation, and the universe, in its silence, invites us to exercise these capacities. The silence of space is not empty. It is full of potential. It is full of questions. It is full of mysteries waiting to be solved. And it is full of the possibility that somewhere, hidden in the vastness, there are other voices, other minds, other beings who, like us, are looking up at their own night sky, wondering if they are alone. We do not yet know the answer, but we continue to search, we continue to listen, we continue to hope. And in that search, in that listening, in that hope, we find something important. We find a connection to the universe and to each other. We find a sense of purpose and a sense of wonder. And we find the courage to keep asking questions, even when the silence does not reply. The question of other voices in the silence is one that will likely occupy humanity for generations to come. It is a question that transcends individual lifetimes and individual cultures. It is a question that unites us in a common endeavor, a shared quest for understanding. And it is a question that, regardless of the answer, enriches our existence and deepens our appreciation for the universe we inhabit. In this chapter, we have explored the question of life beyond Earth. We have considered the Fermi paradox and the various explanations for the silence. We have thought about the conditions needed for life and the search for biosignatures on exoplanets. We have examined the exploration of our own solar system and the ongoing efforts of SETI. We have reflected on the philosophical and ethical dimensions of the search, and we have contemplated what it would mean to find life, or to confirm that we are alone. The silence of space does not give us easy answers, but it gives us something perhaps more valuable: the opportunity to search, to wonder, to imagine, and to hope. It gives us a canvas on which to project our deepest questions and our highest aspirations. And it reminds us that we are part of a universe that is vast, ancient, and full of mystery. As we move forward, we will continue to explore what the silence is hiding. We will turn our attention to the distant future, imagining how the universe will evolve over trillions of years. We will think about the ultimate fate of stars, galaxies, and the cosmos itself. We will contemplate the end of time and the final chapter in the universe's story. And through it all, we will carry with us the knowledge that we are seekers, explorers of the infinite, voices calling out into the silence, hoping that somewhere, somehow, the silence will answer.